Welcome to this EPICURE webinar. It's the second one this year, and today it is going to be about containerization in HPC environments. Our speaker is going to be Theo Prica from IZUM in Slovenia, where the JU supercomputer HPC Vega is located. And Theo has been involved in many Euro HPC projects like Smash. He's an EPICURE member as well. And for example, Masters for HPC. And his focus is his work is also focused on containerization. So that's why he's one of the best people to speak about this subject. Um, just a few reminders for this session. You can interact with the speaker and the moderator and using the Zoom chat. And if you have any technical problems, you can put them there. Please keep your microphone muted so that we don't have noise. Turn it on when you want to speak. This session will be recorded and then it will be posted on the EPICURE website afterwards, so you will have infinite access to it. And that's it. And so I'm giving the floor to Ziga, and you can start. To Theo, sorry, and you can start.
Yes, so here we go. Yeah. So you can see the slides, right?
Yep.
Okay, great. So let's get into it. So thank you for Marcus for introduction. We will cover the basic containerization in HPC environments. As Marcus already said, we are coming from IZUM, which is located in Slovenia, Maribor, where we are hosting Vega, which was the first operational JU system. Additional to that, I would like to acknowledge our affiliate partner on EPICURE project, which is Jožef Stefan Institute. Let's get into it. So the agenda for today is a bit of the context. We will look into the software, containerization, workloads, security, and containers at our HPC Vega, where we apply the best practices. So introduction was already covered, so would a bit skip that, but we will see the MPI and the CUDA GPU accelerated workloads and managing smaller and lightweight environments, such as Conda and so on. Currently, AI in focus, right? Euro HPC is with 13 new AI factories, and call is still open, so future AI optimized HPCs with the specialized hardware requirements. This will bring the industrial users, SMEs, in scope with their workloads, which are quite different than usual HPC environment and workloads and workflows, pipelines, and so on, right? This will bring additional challenges, which are like software integration, codes, and workloads optimization, skill gap on both sides, right? So EPICURE-like projects will play a key role here with covering that skill gap between the industrial users and the other future projects. So software in HPC, right? Scientific software present a challenge itself, right? Lacking of comments, examples, insufficient documentation written by scientists forced to code, lack of support, non-optimized libraries, non-standard installation, and so on, right? So it's challenge itself, and it's covered by EPICURE-like projects. So this brings the isolation here. So dependency hell is present. So it's a common problem, the complex, conflicting, or overlapping dependency in the stack. With right tools and workflows, you can significantly mitigate the dependency issues, ensure flexibility, reproducibility, and scalability. So yeah, software in HPC, right? There are package managers like Easy Build and Spec and Conda. These package managers varies between the HPC sites on the Euro HPC level and beyond. So Easy Build and Easy was already presented within the scope of EPICURE webinars. So the content is available on YouTube already. So additional to that, the system packages and environment models, custom builds from users or sysadmins, and their containers, right? And what is container, right? It's a running process on the file system controlled by host kernel. It's not like VM, but it's more isolated, lightweight, standalone, portable, reproducible, secure, and executable software package. Everything needed is packed in a single image, right? So from configuration codes to dependencies and runtime, everything that's needed to be running that software. So additional, if you would compare a container to the VM, right, virtual machine, there's no hypervisor there. The container have its own layer and can access the file systems and so on, right? But usually the image itself is read-only, and the binding of the user within container is there, and the shell variables and the current working directory is there. So you just need to adjust the configuration about it. So few keywords, right? Definition file, what is? Those are instructions how to make the image, the preparation phase. So if you build the container, there's a compilation and converting this recipe into an image. And then image is compiled container ready to be used. Repositories are placed to store and share those images, right? And then container is a running image of this. But you need a runtime that you can manage those containers so you can execute it within HPC environment. So containerization in HPC offers a flexible alternative software deployment, which avoids conflict. Installation on the system allows the multiple versions of each software. It's comparable to bare metal, right? And the performance-wise, and the container is not VM, right? Embrace technology, but slow adaptation. Convenient option for industrial users and their workflows. Currently, it's integrated in cloud-based HPC, AI, machine learning workloads, and scientific computing frameworks, and beyond. Containerization in HPC offers the portability, deployment, and scalability. This ensures to run the consistency across different environments. Reproducibility, definition file means documentation. Dependency management avoids the conflict of software dependency, brings the user flexibility in scope. But here, just to add that not all JU systems offers that flexibility that allows users to build their containers, but allows user there to copy their software stack, right? The container can be copied on the systems. Performance-wise, it's unlike VMs. Containers introduce minimal overhead, right? So security and isolation is in place. It's up to sysadmins to manage that and to isolate it enough with user privileges, namespaces, and control environments. So containers have come a long way, right? So early concept of isolations are from 70s, and from that convergence of HPC, AI, and cloud is happening right now. So not suitable for all software. Keep that in mind. But containers are not just for HPC; they're in cloud, edge, serverless computing, and as I mentioned already, AI and machine learning workloads and CI/CD pipelines and DevOps and DevSecOps and beyond. So few technologies we would like to bring, which are mostly suitable and used on HPC environments, are Charlie Cloud and Singularity, currently Apptainer, right? And Enroute, Docker, Podman, and Saros. And there are more and more. but those are more, the first two are optimized and can be, I mean, they're optimized and for the HPC workloads, so they support MPI and so, and they're both rootless. In Docker, you need root, but those are more suitable for cloudish environments and system services. So yeah, Apptainer, formerly Singularity, is a container platform designed specially for HPC, MPI, and scientific workloads. It allows users to run containers without root privileges. So features like fake root are there. So users can have the within namespaces they have enabled to prepare the image by themselves on the targeted machine, which is additional optimization added to the additional layer of optimization added to the in scope, right? Ideal for multiple users in HPC environment, simplifies the workflow end to end. It's already integrated in common workload managers such as Slurm, and by their definition, they are secure, portable, encrypted. So what else do we need, right? Fake root to and users will be happy on the system. So common workflow is there the preparation and build of the container by definition file, which we already mentioned is a script, and it's documentation of the container and what is within, so you can look and replace the dependencies if needed. The registry to push a container, deploy a container via job schedulers like Slurm, PBS, and so on. Execute and scale the container runs across multiple nodes, leveraging HPC resources. So images can be brought from the different bootstraps like Docker, Singularity Hub, Apptainer library, NVIDIA container catalog, and so on. That's the definition from the Singularity workflow, a common workflow that you can bring in interactive deployment, development of the container, so you can build it like a image. So it's Singularity image format. It's immutable. Additional to that, you can write it, build it as a sandbox. You can build it from definition file. You can convert it between them. You can build it from different sources, bootstraps, right? Internally or externally, you can use templates. So you can prepare the minimal, so to add the minimal overload of the building time. You can build a base image and then you can build up on top of it. So container execution, and those commands will be covered in the next slides. So for example, here are examples from which I executed on Vega. As we have external network, so you can pull the images from the bootstraps, for example, Docker Hub or Apptainer library, and you can run it on the machine and then execute commands within container or go beyond that, and you can provide, I mean, you can prepare the definition file. Here's an example of it. So you can bootstrap Docker. So this will pull the image from latest image from the Ubuntu, not late. I mean, it's currently latest, but the tag is for 24.04. So there's a PostScript. You add what you want to do with container up above the image itself. So here we update it, install the Python 3 and pip. So additional to that, we installed Torch, PyTorch, and there we added the run script with hello EPICURE, right? And you can run it on the right above screen. You can run it, and then you get the result from the running script. So usually you would add the common software there, path to the execution file, binaries, and you would run it like that, so you don't have to specify the whole path. Then you can build this image from with fake root privileges. You need fake root or root on the system. So it's by definition the root is only for sysadmin, right? So fake root is enabled for the end users. Additional to that, for running the image, you don't need to have the privileges. So running commands within container, you can enter the interactive shell within container. So you can add it to writable sandbox. You can play around it, and then you prepare the image and pack it back. This will be covered in next slide, but interactive shell inside container, you can inspect container, you can extract the definition file if the container was built by it, with it, and then you can extract additional metadata about the container, which are stored within container. So you can, additional to that, you can execute the commands within container that was already mentioned, but here's an example of NVIDIA SME commands running on the login GPU node on the Vega, which can you extract the information from the CUDA versions to the driver versions and utilization of the GPU itself. So yeah, let's convert it, right? So you can convert any image from Docker to Singularity by default, and you can convert the Singularity port immutable CIF image, right? Singularity image format to writable sandbox, and vice versa. So this is very helpful when you have to add some packages, or you want to fix or debug it, right? And build the propagation, so you have a definition file that you don't have to build every time from scratch. And then you have the image. I mean, you have the sandbox, and you can interactively go inside and update the packages, install the new one, debug it, and you have the recipe. Then you add the fixed steps to the definition file. Additional to that, there's a S-Python, which is Singularity Python API, which is working with Singularity containers. Easy installation. Documentation is it's well documented, right? So managing converts from Docker file, for example, and beyond. And you can you can write the Python script and play with interactively via API. And you can execute it, run it, and so on. So additional to that, there's files and data, which needs to be present. That's workflow will work. In HPC environment, where there are I/O and the speed is critical, many small files may stress the parallel system, such as Lustre or Lustre file system. Yeah. A single container file can improve performance. Additional to that, you should optimize your code, which is running on the system, to minimize the file system access, that you don't have locks and so on. Here is advice to use the containers and the environments, right? Otherwise, you will result in performance degradation. So additional to that, you can use bind mounts for a large directories on the host. Multiple binds are allowed per each container, automatically bind home directories and local files. But this is set up. This needs to be configured within configuration. For example, Singularity config is just yes or no for the home dir to be mounted within container by default. And additional to that, you can add overlays and underlays to existing container, which is immutable. So you cannot change it, but you can add overlay image and play with image. So you add additional packages within overlay and then bind it to the container. So you get additional flexibility here. So at large scales in HPC environments, you can leverage scratch directories, local storage like temp, and for high performance workloads with throughput, with high throughput, right? So additional to that, for example, not all GPU systems have the local disk, so that's feature of Vega, right? Because we have a local storage and you can scratch on it and you can squeeze the performance out of the disks. So yeah, the package managers in containers are way to go if you're dealing with a large amount of small files, which can bring the degradation and performance issues in scope. So setting up Python environments within container is pretty simple. So you can avoid re-downloading those packages. You can prepare templates. There's a cache between runs, and here we'll look into three common ones, which is pip, conda, and mamba. And each of these has advantages and trade-offs depending on the workloads. So pip installs packages, right? Pip is well known, but it's very lightweight. You can install Python packages within container or the Python environment, right? It's suitable outside container as well, and it's used as well. It's suitable for smaller environments. You can prepare the requirement file, which is text-based file, and you can just specify what you want to install within container or on the system, right? So additional to the definition file we already presented before, here's the postscript, additional steps, two steps you need to add. So there's additional to that, you install pip through Python 3 model, right? And then install and upgrade the pip. And then you have the binary pip. So you just pip install and the packages you want to install. So here are some data science packages like NumPy, Pandas, and so on, right? Additional to that, you can install transformers and Torch or any Torch Vision and any other packages needed for your workflow. So additional to that, there's Conda, Mini Conda, Anaconda, and all versions of it. So it's very powerful package manager that can handle Python, and system dependency is suitable for complex environments. You can create, activate, deactivate lists, list the environments, create the environment from YAML files. Similar to requirements, it's just different syntax. Example of installation. So similar to before, you just add those steps to the definition file and build a container with it. So additional to that, you need some packages that you can, such as wget, so you can describe the installation script and set the path to the and add the binaries to your path. The re-implementation and drop-up replacement for Conda is Mamba. It performs much faster. It's suitable for complex environments such as Conda, and the interface is pretty much similar. Additional to that, you could avoid updating existing packages. You can freeze install, use the option. Example of here is below. So similar to Conda, you can just create it from the web and from the GitHub repository, install it, and initialize it. So apart from that, the interconnectivity, right? So running Singularity containers with InfiniBand and Slingshot and beyond is you need to know the network topology, right? Or the interfaces, how to handle the resources, files, and memory. InfiniBand and those can be, I mean, the drivers and everything, the stack can be packed in the containers as well. Additional to that, you could use micro benchmark like also to verify the latency. It's recommended that packages which will scale, right, to use the interface like MPI and that are built with PMX and UCX support for better performance and scaling. Requires special configuration to ensure the low latency and high bandwidth. There's an option to allow GPU to GPU communication, to use GPU support on NVIDIA system, there is an additional switch you need to add. It's MV. For the, if applicable, for the AMD system, there is a Watson switch needs to be added, and this will enable the scalability. Will bind the CUDA and the driver support within container, and you need to pretty much match the versions from the GPU point of view and the MPI as well. So here's MPI. Little definition. So it's message passing interface, right? MPI is used for parallelization in HPC environments. It's well integrated within Slurm. So Slurm is built with supported libraries, requires direct host communication. Additional to that, there is a CUDA over MPI, which is MPI built with CUDA. So within NVIDIA HPC toolkits, or you can build you can just build MPI with CUDA, and on the systems it will automatically detect if it's installed or mapped. Alternative to MPI, there's a various implementation like from Intel MPI in one API packages and MPitch and so on, right? Running MPI applications inside containers can be tricky. So there's a network processes management and GPU compatibility needs to be taken into account, and MPI versions within container and outside on the host must match, right? Because otherwise you have issues. And if you want to scale, you need MPI, right? Not for all workloads, but for the CPU and CUDA over MPI workloads. So hopefully you see those slides because it's, yeah, okay. There are a few examples of GROMACs with GPU and MPI support. You can use CPU and MPI combination. You can use hybrid MPI plus OMP, right, for parallelization and scaling exploiting the hyperthreading. But note that some software works better with physical cores and some better with hyperthreading enabled, right? It depends on the software, so there's no unique solution for each, right? And with hybrid mode, you can scale the nodes and request less the resources per node, and the allocation would be much quicker, that you target the few cores per node and then scale it to the multiple nodes. And in some cases, that works better than the other cases. So you can run it with srun and specify the MPI interface, MPI run inside container or within container, right? Debug it via logs, verbose mode, report bindings, GDB, Valgrind, and profiling tools are Liquid, Scorpy, TotalView, Intel, vTune, Nsight, and for NVIDIA workloads and so on. Those are covered within EPICURE project. So if you have issues, you could additionally request to EPICURE support, and we'll look into it. So here are examples of TensorFlow benchmark on the Vega, which was executed for the early stage, right, of the acceptance of the Vega. When you can download the repository benchmarks, and then you can execute it on the GPUs. Example of adding above on top of the PyTorch container, which is currently latest 25.3, you can upgrade it and then install transformers, Jupyter Notebook, and so on within. And in the run script, we added just check that CUDA is available within container and detected. So building container requires root privileges, so fake root or root. You can check the CUDA, if CUDA is available. and then you can interactively run the Jupyter Notebook with GPUs and then run it through job schedule. So additional to that, last year we added the easy support, so additional to the easy stack and the common stack of the HPC site and the national registry on the CERN VMFS. We provide the easy support for both CPU and GPU stack. Yeah, so optimal setup varies per system, right? It's a never-ending story because each system has its own optimized way. So refer to the site documentation, consult with support, or request assistance from us, right? EPICURE application support team. And we'll be glad to help and look into it. So workloads and optimizations. Here are some tips. Use pre-built image, then build on top of them. So NVIDIA, for example, GPU, NVIDIA GPU catalog, right? Those are very optimized for PyTorch, TensorFlow, Nemo, and beyond. Use bind efficiently to mount directories without redundancy. You can use host, pint, MPI, and IB libraries to gain the performance, bind, mount, necessary directories for IB support. Leverage the Slurm, PMX, and UCX for better MPI scaling. Running GPU accelerated workloads using containers. So you can use multiple nodes, multiple GPUs. So there are CUDA, OpenCL, ROCm, and NVIDIA. So you have to, for example, you have to build with specific version. So to gain those features, right? And needs to be built properly so you don't have the segmentation faults and so on. Enables CPU memory affinity, so you can bind processes to cores, to sockets, and beyond. There's a whole documentation within Slurm, you can exploit it, but there's the same optimization tips, right, are doable on the container, right? So if you're running the MPI outside container, you can run it the same way you will run it within container. Or a Slurm option, yeah, if you have, it's just packed, the software is just packed in one file. Set the container and writable temp file system to isolate the workloads. This will prevent the conflicts. Pre-cache the libraries to reduce the runtime, loading delays, and so on. And to get a bit of the security in scope, right? So best practices, security must be enabled at all level of the software. Patches and patch management should be on place. Scan the images and dependency for CVs, misconfiguration, secrets in container, and so on. Those are tools like Claire and Trivi. The next slide will provide the example of Trivi scanning. Use AppArmor, CLinux, CComp filters, and namespaces, right? So keep images updated, minimize the number of installed packages as this brings the additional security in place. Use the images from trusted sources, we already said that, and then sign the images, verify the integrity of image, verify the signatures. Use the immutable Singularity image formats, so it prevents unauthorized modification to the image. Implement access controls, integration with CI/CD pipelines, and tools for automated scanning. Monitor the activity on the host, auditing, and beyond. Use unprivileged user namespaces. So here's an example of the Trivi. It's a lightweight container scanner for Docker and Singularity, sandbox images, containers, right, for security, for scanning for the security vulnerabilities. Above image present the scanning of the Ubuntu latest 24.04 image. There's no detected CVs, but if you download, for example, Ubuntu 20 version, which is quite old, then you have some CVs detection, and you should mitigate and update the image. So this is just a plain example, right? And you can scale from there. So namespace and C groups. Namespaces are a kernel feature, allows each user mapping for the user IDs and group IDs, enable setting up a container without privilege operation. So it's a rootless container, for example, on Apptainer Singularity. User in container can perform tasks without being root. So this provides additional isolation and layer. So namespaces are not just users and network namespaces. There's a lot of different namespaces, be it network, IPC, mount, UTS, and beyond, right? So additional to that, there are C groups, which limit and allocate resources. But in the context of HPC, we would like to highlight two. So network namespaces for managing network interfaces, not really required for the jobs and job submission, but those are more suitable. I mean, additional to that, there are user namespaces, which allows privilege isolation, prevents privilege escalation. They're more safer for multiple user HPC environments and so on. In general, the C groups are used to manage resources. Namespaces are used for isolation of the processes. So this brings us to the final slides. So containers at HPC Vega, we allow user namespaces, so we allow fake root feature. It's not enabled by default, but you need to request it, right? It's assigned. So additional to that, network namespaces are disabled. We are using the C groups version 1. There's version 2 as well, but it's disabled on Vega. This feature is enabled through Slurm, so ensure the resource limitations. Definition files are available for users, as well the pre-built images, such as template for offset stack, so container image available for user to build upon, and so on, right? Additional to that, we embedded the containers within Arc. So this is advanced resource connector, additional layer above Slurm, so you can remotely submit jobs through certificates, and there are runtime environment which enables the containers. So a work in progress is automatic container image deployment and security checks through continuous integration, continuous development pipelines. And images will be available on National Link repository based on CERN VMFS and Harbor. Yeah, containers have come a long way. So they're highly accepted in HPC environment and beyond. So keep the minimal lightweight and maintainable image, keep the security checks in place, keep the sensitive data out of the container, handling many files, use the environments to reduce the system stress, bind data into container rather than copy into it. So, and latest publication rejects the common misconceptions of the performance-wise security and so on, right? And that brings us to the latest slide. So I would like to acknowledge my colleagues which are working on the project as well, from the affiliation partners such as Alia Prach, Sebastian Sterban, Dejan Lesiak. Additional to that, I would from ISOM are Žiga Zebec and Samo Miklac. So yeah, thank you. And time for questions.
Feel free to ask any questions. Let me see what we have in the chat. No questions. Clemens, yeah.
Hi, hello. Hopefully you could hear me. So the question is, what haven't you? Sorry, uh, I know that there was some security issues with user namespaces, and on some HPC systems they were disabled. And could you comment on that? Because
Yeah,
as far as I
there are common, but there are mitigations, right? So I can look into the specific CVS because we wrote a paper about it with Barbara, if you know her.
no, I'm afraid I
Yeah,
haven't
okay.
met her. Yeah.
Okay, so additional that there are mitigations, but as far as I know, most of the JU systems, except for from us, they disabled it. The feature is not enabled.
Yeah,
So
so as far as I know, in case of Cifronet, we have been switching it on and off,
yeah, depending on
several
the
times. And as far as I know, I just check it right now. And I see that they are enabled, but I know that that there was a big problems with the security with the namespaces. And without namespaces, as far as I could
you
remember,
cannot.
there was a pro. I cannot build
Yeah,
I
sure.
could build with fake root, but for example, the how to say it is more problematic to build something with the core libraries of the system. Yeah, you could only build the Python and other stuff, as far as I remember.
Yeah,
Yeah.
yeah. So yeah, additional to that, there's a. I mean, Vega itself is quite flexible on all cases for the users, right? So we enable as much as we want to and mitigate it as soon as possible. And yeah, we are not the largest, but the most flexible HPC, right? Because we, for example, the projects with Leonardo doesn't allow it, and Lumi is using Slingshot. Not sure if all other systems. Not, I would have to check which systems within JU enables this.
But as far as I could understand, if you build a container, for example, on Vega, you should be able to transfer it to other
Yeah,
Euro
yeah,
HPC system. So or you could build it outside in some cloud environment. Yeah, using
yeah,
with the root. Yeah, yeah. Because we have done it in such fashion that when the namespaces were disabled, we just created special. We just take out one of the nodes from the supercomputer to have a builder of the Singularity base containers, and it worked quite well. Thanks. And maybe, do you have any remark about the usage of MPI in the and especially this GPU hour MPI on the in the containers? I saw that you presented quite big amount of information about how it is done, but could you dwell a bit into the specifics?
yeah. I mean, we can talk after this. You can contact me on
Okay,
the mail
okay.
is. I can add the mail and we can chat. But additional to that, I can provide. I can put you feedback that there are a lot of issues around the
Yeah,
CUDA Vera
I know
MPI.
that's the question. Yeah.
Yes, yeah, yeah.
Because, for
Regarding.
example, as far as I could understand and I could remember, you've got these NVIDIA drivers are just hard linked to the Singularity installation. Yeah. So this
Yeah,
minus NV flag points you to one and
it
only driver
will
and one
bind.
and
Yeah,
only CUDA environment, CUDA library. Yeah?
yeah.
And it is still not how to say switch. It is easy to switch between the these variables.
Yeah, you need to play with environments and library paths and so on. Yeah? We have just the example within Epicure. We are calling the project on the Leonardo, and we are facing the issues there with similar issues, and we are solving. But I'm not. Let me say that the team is quite big, right? I mean, there are two affiliates partner. I'm not covering all the topics, right? We just squeeze everything within this presentation.
Okay, great. Yeah, the presentation was great as a not only introduction, but you have given big amount of specifics, and thanks for the presentation. And yeah, and last thing, maybe you know about this because there is something called Docker Compose to automatically build
Yeah.
several, and it used to be the Singularity Compose, but as far as I know, it is dead right now. And do you know anything, any other project that is mimicking this Docker Compose environment or framework on Singularity / Apptainer?
Not as far as I know, but I can look into it. But we use the Docker Compose on the system level, right? Because the few services are running within Docker containers to provide the external and internal services for the ISM and HPC Vega. Additional to that, as you said, everything around Singularity is pretty much dead. The runtimes and so on, right? It's not supported anymore. So that's the split from the Apptainer went. But additional to that, I can look into if there's any options for the composing.
Okay, I'm just asking because, for example, recently we have done some training with NVIDIA and they have great cloud service for that. But if you want to do it on your own cloud HPC service using the Apptainer, you have to play manually with 5 or 6 containers, and they have done it using Docker Compose. So this is the reason for my question because it
Okay.
you could automate things with this Docker, but you know it already. Yeah.
Okay. Glad to know. I will
Thank you
definitely
very
look in.
much for great presentation.
Okay. Thank you for
We
the
have
feedback.
a question on the chat. So, which one do you prefer, Apptainer or Singularity CE?
On Vega, we have the license for the pro version, right? So we have a support, so mutations are quite faster. But additional to that, we support Apptainer as well because we have external services. For example, with another project such as Intertwin, we provide the VM with Apptainer, right? Because it's on Alma based, and we didn't. It would. We would have to recompile the packages. So it's easier to install Apptainer. It's the same isn't interface, but we are flexible. We are using both, right?
So I have a question. For example, how is Singularity support and all that in ARM processors? Is it the same? Are there any?
I didn't even have a chance to look into it, but I would definitely be interested in this topic because I know that Decalion have a ARM, and I would like to. I'm looking into submitting a project just to play around with it because we only have AMD and GPUs, right? We don't have
Yeah.
ARM yet, but future AI optimized systems will be definitely, and the current latest are ARM based. But the support from the Singularity, I think that we are not using it. We are just receiving the mails notification about the latest updates and mitigation for the older versions, but we are currently on the latest version provided by them.
Yeah.
If I could comment, yes. So we've got the GPU partition on Grace hoppers. So we've got ARMs on the CPU side, and as far as I know, the Apptainers work quite well. So we do not use many instances of Apptainers, but I haven't heard any problems with these Apptainers on ARM part of the system. But it is Grace hopper, so it is also quite specific ARM system with these Neoverse V2 cores and GPU heavy, of course.
Cool. Thanks,